Oh, all right, I'm going to make two short videos today about arc length of a curve given by a formula y equals f of x, and then also another video about the surface area if I trace that curve out. All right, so I want to derive the formula. The length of that curve is the integral from a to b, because x goes from a to b, of 1 plus f prime of x squared dx. Or we can write this without introducing that f is integral of from a to b of 1 plus dy dx, square that, and then integrate it. All right, so why is that the case? So let's draw a little picture. I'm going to derive the formula and then do an example. So all right, here we go here. Here's a, and here's b, here's x and y. I want to find the length of this curve here. Okay. Right. So if I think about just focusing on that part, I start here at xi, and here I have xi plus delta x. I'm going to think about I'm going to think about getting the length of the curve by adding together a bunch of lengths of little bits there. So I'm going to redraw that bigger. This is xi. This height here is xi plus delta x. And I get this being the delta x here. And then this length here is, I'm going to call it delta Li. The ith little bit of length. It's not really the change in length, it's like the little bit of length. So I can't just say that delta L, that length there is delta x, because it's at some angle here. So what I do here is I need a delta y, and delta y is about equal to f prime of xi delta x, right? The change in y is the slope of the function times the change in x. Rise over run is f prime of x, the slope. And so I got this essentially right triangle. When delta x is really small, it becomes more and more like a right triangle. So I use Pythagorean theorem, delta Li squared, the hypotenuse squared, is delta x squared, that one leg, plus f prime of xi times delta x all squared. Right? So I solve for that bit of length. Okay. And I get, well, I get the square root of this whole thing. I'm also going to do something. I'm going to factor out the delta x squared. What do I get here? 1 plus f prime of xi squared, a lot of parentheses here. Okay. All right. I think I'm going to do this a little bit differently. Let's rewrite this. Let's factor out the delta x for the right. All right. I get 1 plus f prime of xi squared all times delta x squared. Okay. Here's our little picture. All right. So this length squared is that squared plus that squared, but both of these terms have a delta x squared in. I factor that out. And now I take the square root of both sides. And let's not forget that delta x is positive. So we have delta L, the ith delta L is going to be the square root of that term times the square root of that term. Well, the square root of that term is just delta x. The square root of that term can't really be simplified. Okay. All right. So that length there is approximately equal to, I guess we could put approximately equal to 1 plus the slope squared times delta x. Okay, so I add them all together and I get the length is the limit as n goes to infinity of sum from I is 0 to n minus 1 from this sum delta Li. I add together the first, all these little things here, and let's not forget that 0 is A, n is B, the other first and the last. All right. So this is going to be, I just take that and take the limit that n goes to infinity, and I get integral from A to B of 1 plus f prime of x squared inside the square root dx. Cool. So this is really, the way you kind of want to think about it. This is just the length of a little curve. If I have a little dx here, delta x is kind of like a dx. This is the length of the infinitesimal bit of curve between x and x plus dx. And I just add together all those little bits of length. All right. So I've derived that formula. Let's now do an example. Let's compute the length of the curve y equals x cubed between 0, 0 and 2, 8. And this is a lot like problem 5 on the web work. It's not here it's not stated with the form x goes from A to B, but it's told you x is going from 0 to 2. And that's the important thing in the formula. The 0 and 8 is sort of a red herring in that problem. So let's do that example. So we have y is equal to x cubed. So dy dx is 3x squared, and we have 0. No, not 0 less than equal to x less than equal to 2 is the important part of this. So we get L is integral from 0 to 2 of 1 plus 3x squared, all squared inside the square root dx. If I want, I can simplify that to 0 to 2 of 1 plus 9x to the 4 dx. When I say simplify it, that is not really a lot simpler. In fact, what happens is, I don't know how to do this integral. And I have a suspicion it's not elementary, but we don't need to do it, because what this problem 5 says is basically that's all they want. And on the test, this is what I'm going to want. I'm going to want you to set up the integral to find the length of that curve. And that's what the problems on the worksheet are all about. And frequently, as in this case, I can't do that integral. It's not an elementary integral. It might be, but I don't know how. So what they're asking is, what they're saying is, find A, B, and f of x, so that L is the integral from A to B of f of x dx. That's what this webwork problem asks. Because the webwork doesn't have any way to input this symbol with the integral. So basically that's what they're asking. So the important thing about it is that f of x is not y cubed. F of x is the integrand, the thing you've got to integrate to get the length of the curve. Right? So we see here that A is 0, B is 2, the limits are 0 and 2. And again, as I said, that 8 and that 0 are kind of red herrings, because all we care about is the x limits, and f of x is the thing I'm integrating, 1 plus 9x to the 4th inside the square root. Okay. Yeah, so I know a lot of people make it harder And it is, they just basically just saying, set up the integral. And like I said, I have 3 problems where you set up the integral. And usually, for most functions, I can't actually do the integral. There's a few functions where you can. And one of the basic time when you can do it, the most common time you can do this integral is if the thing inside is a perfect square. So you're taking the square root of a perfect square. But no, with a minus, I could probably do that. But with the plus sign, that's not a perfect square. Actually, even with the minus sign, it's not. But I could factor it. I can't even factor this. So anyway, that's basically it. Okay. There are some examples where by manipulating the thing inside the square root, you can show, oh, that's a perfect square. And then I can get rid of the square root and then I can integrate it. All right. That's about it. So I'm going to do another video about the arc, the surface area if I rotate the curve. Okay.